Hi everybody, my name is Edgar and I'm going to show you my poster about my research work. The title of my work is Improvement of Power Conversion Efficiency in Copper Antimony Sulfide Based Thin Film Solar Cells by Optimizing the Device Structure and Computational Analysis. Here we have our introduction. We have this material, copper antimony sulfide, which is very interesting material for solar cells due to its promising properties. It exhibits an appropriate band gap, high optical absorption coefficient, and P-type conductivity. Currently, the maximum power conversion efficiency of solar cell with this material as absorber layer is 3.22%. And we have two problems affecting the performance of this kind of solar cell. One is the cliff-like conduction band offset at the copper antimony sulfide and cadmium sulfide interface, leading to current recombination trap states near of this interface. And second, the Schottky type molybdenum back content contributes largely to rear surface recombination, lowering further the device efficiency. So we have decided a new device structure where cadmium sulfide is replaced by eco-friendly zinc oxide with sulfur buffer layer, and molybdenum is substituted by ohmic molybdenum oxide as back contact. So we used the numerical simulation through SCAPS-1D, and we have studied the effect of these two modifications on the photovoltaic parameters of the device. Uh, to validate our theoretical model, initial benchmarking of an experimental solar cell has been performed by incorporating a suitable defect model to match the simulation results with the experimental obtained values. Now we have here our methodology, and SCAPS-1D needs several material parameters for each layer. In order to make our simulation as realistic as possible, we took into consideration all information about the absorber layer given by the authors of the experimental cells, properties like band gaps, thickness, absorber density, and a buffer layer higher doped than absorber layer, for example. To make our model more accurate, we consider different defects in each layer and the interfaces. In the case of the absorber layer, we took into consideration the characterization of defects carried out experimentally. In their work, the authors found two deep defects relate to sulfur vacancies and copper antimony antisites, and gave details about those defects like their density, capture cross-section, and activation energies. This is very important. Input all this information into SCAPS. Then we put all this information into SCAPS and we obtain current density versus voltage curves and quantity efficiency curves and the photovoltaic parameters. After this, we propose modification to the original cell structure, this one. This is the solar cell with the highest power conversion efficiency. We propose to replace cadmium sulfide by zinc oxide with sulfur as buffer layer, and also we proposed to replace the molybdenum back contact by molybdenum oxide, which has a greater work function. Now we have here our results, and in figure 1 we have this comparison of simulated and experimental results. In subsection A, we have current density versus voltage curves, and in the subsection B, we have quantum efficiency curves. So in both cases, we can observe a good matching between simulation results and measurements. And this is largely due to the defect model that we consider for bulk materials and the defect at the interfaces between copper antimony sulfide and cadmium sulfide. Therefore, this matching validates our simulation model, and now we can propose modifications to the solar cell and get realistic predictions. In figure 2, now we can see the effect of modify the buffer layer and the effect of different amounts of sulfur. We can see that when we have only zinc oxide as buffer layer, the efficiency of the device is poor, and this curve and this one. However, as we incorporate sulfur by replacing oxygen with sulfur, the current density versus voltage and quantity efficiency curves improves. The optimal amount of sulfur according to our result is with X equal 0.7. Now in figure 3, we can see the effect of replacing the molybdenum back contact by the molybdenum oxide contact. And for comparison, we can see the curves that belong to the initial simulation. This, this curve and this one. Uh, these curves belong to the solar cell with the original structure. And using the back contact with a higher work function than the original molybdenum back contact helps to further improve the performance of the device, as we can see here in this red curve. Then we have in this figure 4 this energy band diagram where we can see the energy and how the conduction and valence band of the different layers that make up our device are coupled. In section A, we can see the band diagram of the original structure and the presence of the Schottky type contact between uh, copper antimony sulfide layer and the molybdenum back contact. Schottky type contact promote the formation of a barrier for charge carriers. This type of contact is because the calculated work function uh, of our absorber layer is 5.4 electron volts and is higher than molybdenum back contact work function only 5 electron volts. And in subsection B, the molybdenum oxide by contact has a graded work function of 6.6 electron volts, and this favors the formation of an ohmic contact, which is characterized by having a lower resistance for the transport of charge carriers. Here in table 1, we can see some physical properties on some layers using the simulation, and in table 2, we have photovoltaic parameters for the experimental simulation, best buffer layer and best buffer layer plus molybdenum oxide as back contact. Here we can see that the highest power conversion efficiency for this new proposed structure is 6.35%. Finally, we have here our conclusions. And the first one, we have validated our simulation model by reproducing the experimental values of a real solar cell. And second, our work can be used for future simulation where copper antimony sulfide is used as absorber layer or as transport layer, for example, in perovskite solar cells. And three, we found that zinc oxide with sulfur as buffer layer can be a viable alternative to replace toxic cadmium sulfide layer by boosting the power conversion efficiency from 3.22% to 6.35%. And for simulated quantum efficiency curves indicate that by incorporating this new buffer layer, the cell improve photoresponse and short wavelength region. And five, our proposed design solve the drawback of shortcut contact at copper antimony sulfide and molybdenum interface by implementing this new back contact, molybdenum oxide. And finally, we have some references and the acknowledgement, especially to Professor Mark Bugelman and his research group at the University of Ghent for providing the facility of the SCAPS-1D for our use. I hope my presentation has been interesting to you. Thanks for watching.